Okay, so hi everyone, welcome to another client talk. This week, Binghui will tell us about the paper with his co-authors on the theoretical limitations of multi-layer transformers, which I think is a paper that Dana brought up in a talk a few weeks ago. So I think it's very kind of on topic that we hear about it this week. I think with that we can start.
Yeah, thanks for the introduction and thanks for inviting me to this seminar. Okay, let me share. Good. Okay. I'm going to talk about my recent work with my co-author Li Jiechen and Hongxin Wu on theoretical limitations of multi-layer transformer. Okay, so let me first give you a quick. Okay, so transformer is the backbone architecture of a large language model, which is used in all current state-of-art commercial large language model. And the focus of this work is on the representation perspective of the transformer architecture. So in particular, the question we care about is what function can or cannot be computed or represented by a multi-layer transformer. So here's the outline of today's talk. And I'll just first give you a very quick overview on the transformer architecture and the problem formulation we use. And then I will talk about our result. And finally, I will give a very high-level overview of our proof and how we derive this result. Okay, so first, transformer. So a transformer typically consists of two types of layer. One is attention layer, and the second is MLP layers. So it's alternating between this attention layer, MLP layer, and then doing this. So in this talk, when I say an L layer attention, I means L. I will view attention layer plus multiple MLP layers as one block. So when I say one layer is really one attention layer plus multiple MLP layer. So when I say L layers it's L alternating between attention and MLP layer. Okay, so the key part for transformer and the key innovation is the attention layer, which I'm going to formally describe in this slides. So in particular, given an input sequence of length n, and assuming each token has embedding dimension d, the output is also of a sequence of n and of the embedding dimension d, where the output at the s position is a weighted average across input positions, in particular a weighted average over the value of each positions. And here alpha ij is the attention probability over token j, and then it's calculated as the softmax. So in particular, it's calculated it's weighted by the exponential to the inner product between the Q value and the query value. So here KQV are just d by d matrix for simplicity. So one missing part from expression is how we obtain the summation, how we do the averaging. There are two popular choice. One is encoder, where you do attention over the entire sequence. Just a second. Okay, sorry for the interruption. Yes. And yeah, so as I said, an encoder does full attention over the overall sequence position. So here the summation just overall positions at the input sequence. So if you think of it as a graph, then the dependence graph is just a complete bipartite graph. Another popular choice is decoder, where the attention is only calculated over previous token. That is, at position I, it only attends tokens that appears before position I. Okay, and if you think of it as a dependence graph, then it's like some autoregressive nature. So each token only depends on previous token, but not future token. Okay, there are many more like empirical details of modern large language models, including people use multiple attention heads, people use different tokenization, position coding, and also the MLP layer could be a bit different, like depending whether you use a mixture of experts or some layer normalization and what activation function you use. But actually, for our purpose, if you think in particular, when you think of a representation power, this details are actually not that important for our result. So our result could cover all this in empirical details. But there's one thing that really matters, and that's also introduced in my previous slide, is whether you consider encoder or decoders. So the original transformer paper actually proposed an encoder and decoder architecture. Later work like BERT uses encoder-only model, where just to remember, encoder means the attention is calculated over the full sequence. But more recently, modern language models, starting from GPTs and also language model by other companies like Gemini, Llama, or DeepSeek, they are all decoder-only. So they are also trained using autoregressive ways, and the attention is computed only over previous sequence. So there's historically, there's a shift from encoder-only model to decoder models, and our modern language model using decoder-only model trained with next token predictions. So because of this, the focus of this work is on decoder-only transformer, and I also briefly mentioned about encoder in some later part of my talk, but the main focus is on encoder-only model, decoder-only also. Okay, so next, let me go over the results. And before that, let me just briefly describe the model we're considering. So here we think of a transformer as parameterized by 4 parameters. The first one, HH, which is the number of attention heads. D, which is the embedding dimension. P is the precision. Is the precision, which is the number of bits you need to the number of bits you need to store the weight of your neural network. Just one. Precision essentially means the number of bits you need to store one weight of your neural network. And finally, L is the number of layers. Okay. So here we adopt a circuit view and think of a transformer describing a mapping from its input sequence, particular x1, x2 to xn, to an output answer, where the output is just determined by the output of an MLP layer in the last layer. Okay, the embedding in the last position of the last layer. Okay. This is a very just classic and standard formulation, and the advantage of here is that it captures a one-step computation of transformer. It's suitable when you think of transformer as oracle or reward model, or if you just want to think about the computation of just one step. But also the disadvantage here is that it ignores inference time scaling. So in particular, this formulation does not capture the chain of thought paradigm. But I will talk about this, briefly mention this, and talk about some of the implication to it in later part of my talk. Okay. Okay, so here's the formulation. So we essentially just consider last token prediction. We assume it's an input sequence and want to determine the output of the next position. Okay, so now under this formulation, let me briefly describe what has been done in the literature. Actually, I think a lot of the work actually been done by this community. Okay, so first, the power transformer, that is what task can be solved by multilayer transformer. So early work starting from a certain like a regular language or programming language, and then later people also think about representation power for transformer performing in-context learning and so on. Also, there's another line of work trying to demonstrate some advantage between transformer and the traditional sequential modeling like RN or STM. So from a very high level, the idea is for any given task, you can try to give some construction of the transformer circuit and showing actually transformer is a quite good parallel architecture, and it can represent certain like regular language or perform some algorithms in context learning. Yeah. Okay. So The second part is about limitation. That is, what task cannot be solved by transformer. So here we have a very good understanding for one-layer transformer, and many more have developed unconditional lower bound for one-layer transformer. Here, when I say unconditional, I mean a lower bound that does not rely on any like unproven conjectures. So here, people have proven like one-layer transformer actually fails to solve tasks like three-sum, two-function compositions, and induction heads. So the most natural question then one should ask is like, what about multi-layer transformer? Because the transformer used in practice are really have multiple attention layers. So the question is whether one can extend this lower bound to multi-layer. So I think even start from a very early work by Michael Han, there's some speculation maybe there's some circuit lower bound barrier, meaning that if we want to prove some lower bound for multi-layer transformer, then you must first prove some lower bound for certain circuit family, which might be challenging and open for many years. So I think because of this, and also because the hardness, the challenge for proving lower bound to multi-layer transformer, prior work mostly relies on certain like computation complexity conjecture. For example, people have shown that a transformer, the computational transformer, can be captured by threshold circuit or log space computation or like massive parallel computation. And because of this connection, people can rely on existing computation complexity conjecture. In particular, if you can, if a problem is hard for certain circuit family like TC0, then it's also hard for constant depth transformers. Okay, so I think the main question we address in our paper is to give the first unconditional lower bound for multi-layer transformer. So here's a formal statement of our theorem. I will give more explanations later and more applications later, implications later. So our theorem states that for any constant L, we prove that an L-layer decoder-only transformer cannot solve L-step sequential function composition whenever the model dimension is less than n to the 2 to the minus 4L. So here I call this h times d times p the model dimension. Recall like h is the number of tension heads, d is the embedding dimension, and p is the precision. Okay, so essentially our result saying if you think of this the length of the sequence as a growing parameter, our result showing like asymptotically once it goes above certain threshold, your transformer can now solve sequential function computation task. And so from this asymptotic view, we prove that L-step composition requires omega L layers of a transformer. Okay, so let me explain the task we're considering, which we call sequential function composition. Formally, it's defined as follows. So that's parameter L. And L's sequential function composition involves L function, F1, F2 to FL, and then a query W. And you can think of this W as consists of L part. So we sequentially the answer is defined inductively, or actually the computation of the answer is defined inductively. So it involves L steps of computation. Particularly first, you compute I1, which is F1 applied to W1. And I2, the second index, is defined as F2, the second function, applied to W2. And the I1, which is the index you obtained in the first step. So in particular, at L step, the L's index IL is determined by the function FL, and then the query WL, and then the index IL minus 1 computed in previous one. And finally, the goal is to output IL, the L's index. So in the task, we assume the function F1 to FL is given explicitly, meaning that the prompt consisted of the truth table. of this L function. And in particular, we put the input prompt, make it explicitly describe the function in the reverse order. That's we first present the function FL by presenting a truth table, then FL -1, and so on to FL1, followed by the query, the final query W. Okay, so let me give you a simple example to illustrate what's exactly this sequential function computation task. So here in this simple example, I will consider L equal to 3. And so recall the query W consists of 3 parts, W1, W2 to W3. Here I'll just set it to each part to be either 0 or 1. So there are 3 functions, F1, F2, F3. And here, recall like I1 equal to F1 applied to W1. So here, I'll assume F1 is a mapping from 2 to 2, from domain size 2 to domain size 2. So for the second function, its input takes two arguments. The first one is W2, which is either 0 or 1, or I1. So the input of the second function actually has domain size 4. And here we also assume its output has domain size 4. Similarly, for the third function, the input consists of 2 parts. One is W3, and the second is I2, the index derived from the last step. So W2 is either 0 or 1, and we assume I2 is either 0, 1, 2, or 3. So here, this means the input domain of the third function has size 8, and we also assume its output has size 8 for simplicity. So as we said, we present the prompt in the reverse order. We first present the truth table or describe the F3, then F2, F1, finally to W. And in this example, let's assume W equal to 1, 0, 1. So W1 equal to 1. This means in the first step, you should, okay, and in this animation, I'll use green color to denote 1 and the yellow color to denote 0. Okay, so in this example, because W1 equal to 1, so you should follow the green arrows. So you should look at the second position of F1. And let's say the second position of F1 is 0. Then in this case, by the definition, so I1 equal to 0, and also we know that W2 equal to 0. So you should really look at the first, the yellow arrow of F1. So in particular, here, because I1 equal to 1 and W1 equal, I1 equal to 0 and W2 equal to 0, you should look at the first position of F2. Okay. And let's assume I2 equal to 2. So here, in order to perform the third computation, we know that W3 equal to 1 and I2 equal to 2. So you should really look at the sixth position of F3, and that's the output you require the model to answers. Okay. I hope this gives you a rough idea of how is the composition task we're considering. And so let me here give you a very high level description of the intuition. So the high level intuition is that when important information is presented at the end of the sequence. So in our case, this query W is important represented at the end of sequence. Then autoregressive model fails to retrieve information efficiently. So in particular, recall like in our example, this F3, F2, F1 has exponential increasing size. This means a really large part of the prompt is F3, which is presented in the first part of this prompt. And then there's a lot of computation down over positions corresponding to F3. But because of the autoregressive nature, this computation is just irrelevant to later part of the sequence. And this means a lot of computation just spent on input that's just does not really contain any like useful information in some sense. Okay. I'll go to the technical part later, but here's a very high-level intuition. So the intuition is that because of the autoregressive nature, lots of important, if the important information is presented at the end, then you might waste a lot of computation in the first part of the sequence. Okay, so now let me go back to the result, and based on result, I will show you several implications of our main theorem. The first implication is on depth width trade-off for transformers. In particular, we have the following depth width trade-off. For sequential function computation task, we know that L+1 layer transformer actually could require exponentially small width than L layer. This is because this trade-off is that for L sequential function computation, we have proved that L layer transformer requires polynomial dimension. And also you can easily construct an L+1 layer transformer that solves this L sequential function composition task using just polylogarithmic number of parameters. So this demonstrates some exponential depth and width trade-off for transformer. So here, the empirical observation is that if you only consider pre-training loss, that is, if you average over all the predicted tokens, then depth actually seems not matter too much due to this scaling law paper by Kaplan. But if you consider some reasoning tasks, say like grade school math and some computation tasks, where sometimes it's really important to predict some single tokens, some pivotal tokens, the depth is actually more important for this task. And this is also this is evidenced by some empirical research. So the second implication is on the encoder versus decoder. Here we saw some exponential separation between encoder versus decoder. In particular, we proved that an encoder could solve this L sequential function computation task using only log L layers and polylog N model dimension. Okay, so this is in sharp contrast with decoder, where if it has no more than L layers, then they need polynomial number of dimension. So this shows that the impressive power of encoder and decoder could actually be quite different. And I think some of the aspects may not be aware by some early work in the research committee. And for encoder, in fact, we actually show some circuit lower bound barrier for encoder. So we prove that depth L into the 1 plus epsilon where symmetric circuit can always be simulated by an L layer, order of L layers transformer with model dimension into the epsilon. So this steps L into the 1 plus epsilon where symmetric circuit is usually called just like superlinear size symmetric circuit, which is some circuit family class. And for this class, people already for this class of circuit, it's already hard to prove any lower bound. Actually, no non-trivial lower bound was even known for linear where depth 3 symmetric circuit. So this means there's actually some circuit lower bound barrier for encoder. Because if you can prove some lower bound for, let's say, depth 20 encoders, then it would imply some lower bound for symmetric circuit, which actually people do not know how to prove right now. Okay, and also like symmetric circuit here is that it's kind of similar to the circuit consider there's a unbounded fan-in, but there could be a symmetric function placed on each gate, meaning that at each gate, the output is a deterministic mapping from the sum of its input to its output. Okay. Okay. So finally, we also also briefly talk about the chain of thought and show what's the implication of our result. So roughly speaking, chain of thought is kind of like a paradigm proposed in work by Jason Wei and others. So by now it's well known that step-by-step reasoning could elicit much stronger reasoning capacity of language models. And so on this side, previous work actually proved that transformer with chain of thought could simulate any polynomial time algorithms of circuit. So by doing this, so because previous work also showed like the computational transformer is lies in TC0. So because this, as long as TC0 not equal to P, transformer with chain of thought could have much stronger representation of computational power than just single token prediction. So the position of this work is that we show some provable benefit of chain of thought because like this L sequential function composition can be easily solved by an L step of like computation, meaning like L step chain of thought. Okay. Okay, so let me finally go to the technical part and give a high-level overview of how we derive this result. So here's a high-level outline of the proof. So the first part, we will introduce a new communication model, which we call autoregressive communication. And we prove that by proving communication lower bound in this autoregressive communication model, then it would directly implies lower bound for underrepresentation power of transformer. And the second part is more technical, which we actually prove some communication lower bound on this model. And our main technique is called indistinguishable decomposition. So in the part of in this talk, I will mainly focus on the first part. That is, I will introduce what is autoregressive communication model and why lower bound in this model transform to lower bound of transformer. Okay, so let me introduce the autoregressive communication model, which is a multi-party communication model. So we assume there's a capital N number of players where each player receives Zi as input. So here, this capital N actually does so here Zi does not necessarily be like 0 or 1. Zi could be of different lengths. Okay, so different player could receive very different input. So there are L epochs of communication, and the communication proceeds one epoch by epoch. So in the L's epoch, the communication proceeds as follows. For the ith player, it will send a message gamma ij to previous player j. So when I say previous player, I mean players as index greater than I. That's I plus 1, I plus 2, or I. So here in the else epoch, for each player, it will send a message to previous player j. And then the previous player, based on its own information state, which is defined indirectly, but roughly speaking, is the amount of information it told of what player j knows. Based on its information state and the message gamma ij, that's the message obtained from player I, it replies a message gamma pi ji. So here the information state is inductively defined. So initially, it just player J's own input, but later, because it received message from other players, its information also grows. So finally, in particular, the information state of the ith player at L's epoch is defined as the union before of the information it obtained before L-1 layer, and union the message it received from our previous player. So here, if you look at the full split, the player I will send message to previous player, kind of like some query, and then previous player will return message. So player I will include this message into its information state. But importantly, we know that this information state of player I is updated to include our message received from previous player, but it does not include message obtained from players appear later than player I. So in particular, it does not include the transcript from I-1 to I-2 to 0. Okay. Okay, so let me give you some examples. And in these examples, we assume there are 4 players and there are 2 rounds, 2 epochs of communication. Okay, and here there are 4 players, so they receive Z1, Z2, Z3 to Z4. So in the first epoch, so recall like each player will send some information to previous player and get message back. So here, starting from player 1, it sends message gamma 1 2, gamma 1 3, gamma 1 4 to previous player. And this message only depends on player 1's input Z1. Then Z2, Z3, Z4 will reply with some message. For example, the fourth player will reply with message pi41, which depends only on its own input Z4, and then the message sent from the first player. Similarly, the message sent back from the third player depending only on Z3, and then the message sent to the third player, and similarly. Okay, so at the end, the player 1 would include its own input Z1 as well as the message gathered from previous player. Now move to the second player. The second player Z2 would send message to player 3 and player 4. So importantly here, this gamma 2 4 and gamma 2 3, that's a message sent from player 2 to player 3 and 4, depending only on player 2's own input. So this okay. So the second player actually receives some message from the first player, right? Because in order to determine pi to 1. But here, in our model, the most important feature is that this model is only used for the query purpose, and the second player actually does not remember it. So when second player perform the computation, it sends a message to previous player, and this message actually does not depend on what's been sent from player 1. Okay, and also similar for players 3 and 4, it will reply some message, and here the fourth player message will depend only on its own input, and then the transcript sent, the message sent from player 2. Okay, and finally, the second player will update the information state by including both Z2 and then the message sent from 3 and 4. So finally, player 3 and 4 have some communication. Player 3 sends gamma 3 4 to player 4, which depends only on its own input. And then player 4 sends back some transcript, which depend on its its own input, as well as the query message gamma 3 4. And finally, player 3 updates the information state by including its input Z3 and then the message from player 4. And then the last player only updates, actually its information state is not updated. And this is one epoch of communication. And you can do the same things by replacing Z1 with X1 and Z2 with X2 and so on, so to do the second epoch of communication. Okay, so here's the reduction, which is actually once you set out the model, the reduction is actually very similar to previous work. So the reduction is that we prove that if a transformer a parameter HDPL would give the deterministic communication protocol such that the communication between player I and the player J just scale linearly with player I's input size. So recall here gamma ij and pi ji is just a communication between player I and two player I and j. And so in particular, reduction says if you have a transformer, then it gives you a deterministic communication protocol such that the communication between I and j is roughly of order zi, like the number of bits for zi times HDP, which is the model dimension. So here's a very high level proof sketch. So the idea is kind of similar to previous work. So player I just send the so in order to we want this player to simulate the computation of transformer, and in order to simulate it, the player I would just send the query value at the else layer, and this query value just it just corresponds to the tokens in Zi. Okay, and then player J just return partial sum which yeah. Okay, actually, there's some typos here, but the player J would just returns the partial sum, which corresponds to the computation of the attention probability, also the average weighted average on the value. Okay, and you can prove that the number of bits being sent between I and J is roughly Zi times HTP. So HTP is roughly the number of bits for each term, and because they are Zi tokens, so each token roughly corresponds to HTP bits, and they're Zi tokens, so the total number of communication is roughly Zi times HTP. Okay, that's reduction, and now let me go to the second part, which is actually the more technical, the technical part. But I'll just only give you some very high level overview of how we really prove lower bound in this model. So recall, like in the first step, we proved that in order to derive some lower bound for multilayer transformer, you only need to derive some lower bound for this autoregressive communication model. So first, why we expect sequential function computation is hard in this model. So recall the sequential function computation involves sequentially computing L indexes, where the L's indexes is determined by the previous index as well as the L's query. So the idea is that without knowing the value of the L's index and the query W, then the communication among FL plus 1 to F capital L, it's just kind of like useless because actually there's a lot of computation or communication. There's a lot of communication done between these pairs, but because it does not know W and L, so their communication in some senses is invariant to the value of W and L, so their communication is not that useful intuitively. This is kind of similar to the round elimination technique in communication complexity. So, so how we actually prove the lower bound? So here's a very high-level overview. So the idea is we found some indistinguishable composition, which is defined as some two sets, which is defined as two sets of the input, where we denote as R and Z. So here R means some assignment of to player L to capital L, and Z is some assignment to player 0 to player L. We found such assignment such that for every input from ZL and every assignment to RL, the communication leads to the same transcript. So if player 0 to L receives Z and the player L to capital L receives some R, then their transcript are always the same. So this means under these two assignments, they are kind of indistinguishable composition. We required the size of the indistinguishable composition is large, and also we wanted to have a large coverage on L-1. So intuitively, this means if you can find such composition, then it means after L runs the computation, there's still a lot of uncertainty about the input of player L to capital L. And also at the same time, if they also have very large coverage on the L-1 index, then it means you have very large uncertainty on the L's index. Okay, so let me quickly finish up the talk and just give you some takeaway message of this work. So we proved the first unconditional lower bound for multi-layer transformer, and part of the decode-only transformer. It has implications on computation tasks, depth width trade-off, and some architecture separations. So the key conceptual idea we introduced is the autoregressive communication model, which is actually a new communication model, and we believe it captures well about the autoregressive communication nature of decode-only transformer. And also we propose in order to study the communication model transformer, it's crucial to study this new communication model as it gives stronger and unconditional lower bound than previous work. And finally, in terms of technique, we developed some technique which is called index-signal composition, which certainly inspired by classical ideas from the literature, but I think we may need more. And I think we want more new techniques for this model in order to prove a stronger lower bound. Okay, yeah, I'll wrap up the talk here and leave the rest time for like questions and discussions. Thank you.
Thank you so much. Okay, I will stop the recording.